Hello, hello. Got another fiddler for you. And this one, I think it's quite a bit easier than other fiddlers I've done, or maybe it's just right in my wheelhouse. But anyway, this should be a fairly straightforward one, although there are some interesting little math bits that I'll try to go into a little bit more detail on. But anyway, let's get into it. So this is based on a Super Bowl play where I guess the 49ers won the coin toss and people are criticizing them for choosing to go first. And so this is a very simple little game theory model to try to simulate whether going on offense or defense first is an advantage. And this kind of highlights the advantage of, well, it's eventually going to highlight the advantages of each, but because of the simplified numbers, it will come up with an answer. Anyway, the first version of this question is very simplified. It basically says you have no choices. You're just going to go ahead and try to score, and there's a 1/3 chance of either scoring a touchdown for 7 points, a field goal for three, or not scoring at all. Now, you might think that 7 and 3 are very important here, although it turns out in this game it really doesn't matter. Like, it matters that 7 is more than 3, but if these were 7 and 6 or 4 and 3, it really wouldn't make any difference at all to the model, which I thought was a little bit interesting because we're not doing anything about expectations. It's just who's going to win. So anyway, um, both teams get a chance to score, and then if there's a tie after that, what's going to happen is if you're going to alternate possessions again, and the first team to score from that point wins. So it's a little bit different than how things used to work, but that is the current state of how the game is played, roughly. I mean, obviously the chances of getting each of these scores is just made up, but the basic outline of how the rules work is more or less accurate. So um, so I'm going to think about this as dividing into two phases. In phase one, both teams get a chance to score, and then if we get out of phase one with a tie, we'll go into phase two where you alternate until a team scores. So that's the way I'm going to think about it when I talk about phase one. I'm talking about when both teams get a chance, in phase two, about that alternating phase. So if we want to figure out the probability of winning for me as the person who's going first, well, I can think about it. I'm either going to win in phase one or I'm going to win in phase two, right? And so my probability of winning overall is just my probability of winning in each of those phases. And since there's no situation in which I win in both phases, I can separate those out and say that it's just the sum of each of those probabilities. And just a little notation thing here. When I say P and then in parentheses something, that means the probability of whatever is there in parentheses. So what about phase one? Well, you could enumerate all the possible scores. There are only 9 of them, so it doesn't take that much to do. You could do a little bit of grouping to make this a bit more efficient by saying, if I score a touchdown, what's my probability of winning? It's 2/3. If I score a field goal, what's my probability of winning? Well, it's 1/3, right? And then you have to think about your probability of tying. So it doesn't really save that much time, but you would save a little bit of time if you thought about it a little bit more um, algorithmically rather than enumerating every single possible outcome. But here I'm just going to enumerate all the possible outcomes and note that of those 9 possible things, which all happen with equal likelihood, because in this simplified model, what the second team does has no bearing on what the first team does. And so my probability of scoring 0, 3, or 7 points on the second drive is unrelated to what the first team did. Then I end up with a 1/3 chance of winning, a 1/3 chance of tying, and a 1/3 chance of losing after phase one. So what about phase two? What's going to happen here? Well, so what's going to happen on a tie? Anytime I get the ball or the other team gets the ball, I'm going to have a 2/3 chance of winning. Why 2/3? Because I'm going to win if I get a field goal or a touchdown. Either one is going to be a win. So the sum of those probabilities is 2/3. So with 2/3 chance, I'm going to win if I have the ball. But there's a 1/3 chance, not that the other team wins, and it's important. There's a 1/3 chance that the other team gets an attempt, right? They'll get an attempt. And then from there, they're going to get a 2/3 chance to win. And then there's another 1/3 chance that it comes back to you, right? So, and this is going to keep repeating and repeating over and over and over again. So this is going to make it a little bit tricky to figure out what the probability of winning is because we need to do some, kind of late high school math. But before we get to that, let's think about some conditional probabilities. right? And what I mean by conditional probabilities are what is the probability of something given that something else occurs. So if I talk about the probability of A conditional on B, what we're saying is assume we're in a situation where B has happened. Given that, what's the probability that you get to A? So as an example, what's the probability that I win on my first attempt in phase two? Of course, getting conditional on getting to phase two. Well, that's just 2/3, right? That's if I get that field goal or that touchdown, I'm going to win. Otherwise, I didn't win on that first try. What about winning on either my first try or my second try in phase two? What's the probability of that? Well, now I have to think a little bit carefully about each step here. So there's the 2/3 chance that I win on the first drive. That's still there. But I need to add something else. What I need to add is the probability that I win on my second try. What is the probability of that happening? Well, I have to give it. I have to lose on the first try. So that's that first 1/3. And then the other team also has to not score, right? They have to not score as well so that the ball gets back to me. So I even have a second try to begin with. And that's another third. And then on my second try, then I'm going to score. So the 2/3 chance of that happening. So if I add all that together, multiply and add it together, I end up with that 2/3 plus. And I didn't add this. I could have, simplified this a bit more, but we're just going to say, this 2/3 plus 1/9, which is those two 1/3 multiplied together times another 2/3. I'm going to leave it like that, and you'll see why in a second. Because now I'm going to ask this other question. What's the chance of winning on my first try or my second try or my third try in phase two? So now I'm thinking about, I'm trying to get eventually towards what's the probability of just winning in phase two. And to get there, I'm going to add in, each possible attempt I might conceivably get was the probability of winning on that attempt and kind of adding it into the probability. So if I do that, I get that same 2/3 plus, 1/3 times 1/3 times 2/3. Those first two terms are exactly just the probability of winning my first or my second try. So what is the probability of winning my third try? Well, on my first try, I've got to not score. It's got to go to the other team. They have to not score. It comes back to me. I don't score on the second try either. That's another third. And then it goes to the other team. They don't score again. And then it finally gets back to me and I score with a probability of 2/3. So all of those things have to happen for that third try. And I can just add those together again, since winning on my third try is totally mutually exclusive from winning on my first or second tries. I can just add those probabilities together. And I'm going to leave this again in another kind of not totally simplified way. I'm going to leave that 2/3 as it is, that 1/9 times 2/3 just like before. And then I'm going to take each of those 1/3, each pair, and put them together into a 1/9 and say that's 1/9 squared times 2/3. So why am I doing this? Well, hopefully you're seeing a pattern here where every time I add in another attempt, I'm basically multiplying that probability by 1/9, 1/9 being the probability that I don't score and the other team doesn't score, right? Both of those things happening. And then that's going to be the kind of probability of winning on that try in phase two. So if I want to know what's the probability of winning on any possession in phase two, right? It's just going to be 2/3 plus 1/9 of that, plus another ninth of that, plus another ninth and by another ninth of that, I mean, right, 1/9 times the other thing, which already got a 1/9 in it, right? So this 1/9 keeps stacking and stacking and stacking here. And, if you remember this from high school or maybe you're not in high school yet, or, whatever if you've seen this math before, it might ring a bell that this is what's called a geometric series, where I have some base number, in this case 2/3, and I'm multiplying it by the same number over and over and over again and adding the results together. So a quick little primer on geometric series, right? So if you want to know if you just want to know the answer to how you do a geometric series, it's just this formula, right? S is A over 1 plus 1 minus R, where A is the value you start with, and R is the fraction that you're multiplying that by over and over again. And if R is less than 1, this will converge, and it'll just work. But before we get into what the answer is, I want to try to give a little bit of intuition for what's going on in these geometric series. And for me, the most intuitive way to think about it is with the fraction half and starting with this kind of unit box. So if I have this unit box, right, I can think about taking half the box and adding it in there, right? So the left half of the box, I'm shading now in blue and saying I've filled in this box with 1/2. And now what I'm going to do is take half of what's left over and add that in as well, right? So I'm adding half of what's left, or another way of saying that is half of the previous thing, because what's left and the previous thing are kind of the same, because I'm doing this in a half. And I can fill in, another half of what's left. I can do this over and over again and keep going. And if you might have the intuition here that eventually, I mean, not actually eventually, but kind of in the limit more precisely, this box is going to fill up, right? That the box will be completely filled by the end of this process, if you think of this process as having an end. I mean, in reality, at no particular point in time will I actually get to the end, but in the limit, as I put an infinite number of boxes in there, I will approach a point where this box is just completely full. And this is going to be somewhat related to Zeno's paradox. Actually, it's very related to Zeno's paradox. And so Zeno's paradox, as described by Aristotle, at least as translated by somebody that translated the physics, says that which is in locomotion must arrive at the halfway stage before it arrives at the goal. And the basic idea here is, okay, imagine that I'm a person and I'm trying to reach the end of this race or goal or whatever it is. Then I can subdivide space, right? And I can say, well, in order to get there, first I have to get halfway there. And that is an action that takes some amount of time to do, right? But once I get there, I can say, well, I can just go halfway again, and that's another action that will take some other amount of time, right? And Zeno, it's not exactly clear to me whether Zeno meant this. I mean, I'm sure in the end he understood that motion exists, but the way that is often phrased by later philosophers is that Zeno claimed that motion could not possibly happen according to this logic because you cannot do an infinite number of things. My intuition tells me that this is more of a tongue-in-cheek kind of explanation, and not that Zeno actually thought that no one really moved, because we so plainly do move, but instead maybe a way of prodding us to think a little more carefully about this. And it didn't take very long. I mean, Aristotle lived maybe 100 years after Zeno and already kind of figured out why this isn't a paradox, which is basically that if you can subdivide space into an infinitely divisible number of parts, you can do that with time as well. And so the amount of time it would take to do these little steps going halfway toward the goal gets smaller and smaller. And as you and then, so if you think about the total amount of time it takes to get there, yeah, you're doing an infinite number of things, but the time it takes to do each thing gets smaller and smaller. And so you actually can do a supposed infinite number of things if those things get smaller and smaller. And that's basically a, baby's first limit. Anyway, this comes back to our geometric series, and in the problem, our specific problem, remember we're trying to figure out the probability of winning in phase 2, where we started with a 2/3 probability on the first attempt, and then we're multiplying by 1/9 each time. So our A is 2/3, our R is 1/9. We plug this into the formula, and you'll get 3/4. So basically, if I get to phase 2, I have a 3/4 probability of winning, right? And as a note, if you start with A as a half and R as a half, you will also end up with S equals 1, right? In other words, if you start with half the box full and you add half of the size of what you've filled up just in the previous step over and over and over again, you will end up with 1, meaning you will kind of in the limit fill up the entire box exactly. Okay, so back to the original problem. What is the probability of winning? It's the probability that I win in phase 1 or in phase 2. And I'm going to do a little bit more on conditional probability here. So one more notation thing, this vertical bar is the conditional on. So I want to think about what is the probability that I win in phase 2, conditional on getting to phase 2, right? That's actually what I calculated before. I didn't calculate the probability of winning in phase 2. I calculated the probability of winning in phase 2, conditional on getting there, right? And if I want to know that more broadly, I need to do some conditional probability. And there's this rule in conditional probability that if I want to know the probability of two things both happening, I could look at the probability of, so the probability of A and B both happening is the probability that A happens, given that B happens, times the probability that B actually did happen. And this is just a consequence of the probability, right? So if you think about what's the probability of both things happening, well, you could think about them as kind of sequential. I mean, it doesn't have to be literally sequential in time, but you could think about, well, what's the probability that I get one thing, and then use this conditional probability, which says, well, given that that happened, what's the probability that I get to the thing that I want? And if B has already happened, and then A happens later, then you can say that A and B both happened. And so that's a way of breaking down this joint probability. And another way of saying what's the probability that I win in phase two is that I win in phase two and I get to phase two, right? There's no way to win in phase two without getting to phase two. So adding this kind of joint probability doesn't change it at all. And now I can use this conditional probability rule to say, well, that's the probability that I win in phase two, conditional on getting to phase two, times the probability that I get to phase two. So my probability of winning becomes the probability that I win in phase one, which we decided was a third, plus the probability that I win in phase two, which is 3/4, the probability that I win in phase two, conditional on getting there, times the probability that I get there, which is just the probability that I tied in the first phase, which is a third. And if I add all that together, I'll get to 7/12. So that's the answer to the first step of the Fiddler this week. There is an extra credit. And if you're like me, you maybe thought, well, this is really silly because what happens to the second team's probability of a field goal if the first team scores a touchdown, say? Because if they score a touchdown, there's just no reason that the second team would ever kick a field goal. But in the first phase, I'm going to try to reserve first phase for the problem. In the main question, we just assumed all that away. We said they have a scoring distribution. No one's doing any strategy. We're just playing. So now we're going to think a little bit more about some alternative strategies. And so in the extra credit, basically, what I said before happens. If we get a touchdown, there's no way the defense is going to go for a field goal. So instead, they're going to go as aggressively as they can and try to get a touchdown. So now we're going to have two possible strategies that either team can use in any phase and any possession of the game, which is that if you're an offense, you could do the normal 7-3-0 split like we had before, or you can do a more aggressive strategy that, it's touchdown or bust. And we're going to say that there's a 50-50 chance of getting a touchdown or not in that strategy. So again, we're on offense first. What's the probability that we win? Now in problems like this, so this is a very kind of basic game theory problem. It's often useful to start at the end and go backward toward the beginning. So what I mean by that is think about what would a team do at the end of the game and then work backwards to decide what they will do. Because if you can figure out what they'll do at the end, then when you go before them, then you can say, okay, what should I do given that I know what they're going to do, right? And you can use that backward induction logic to figure out what you should do at the start. So we're going to start at the end, and in phase two, what is everyone going to do? Well, they're going to play normally. Why do I know they're going to play normally? Well, I know they're going to play normally because if they have the ball in phase two, the only thing they care about is, do I score or not? And if I think, do I score or not, the probability of scoring playing normally is higher than the probability of playing aggressively. Because the probability of scoring if I play normally is 2/3, and the probability of scoring if I play aggressively is only 1/2. So in phase one, what am I going to do? And specifically, what is the second team going to do? Because they go last. So I'm going to think, if I'm working backwards to this problem, I'm going to ask what the second team does. And that depends on, now we have to be careful here. It doesn't depend on the strategy you choose, right? The strategy you choose is actually irrelevant. What it depends on is what you achieve. In other words, whether you scored a touchdown, a field goal, or you didn't score at all. And so we can think about each kind of possible scenario and think about what the other team might do. And if you score a touchdown, they're going to go aggressive. Why are they going to go aggressive? Well, again, as we said before, there's no reason to go for a field goal because a field goal is going to lose, right? And if you don't score at all, they're going to play normally for the same reason that if you get to phase two, you're going to play normally. I mean, if you don't score in phase one, from the second team's perspective, they're kind of in phase two already, right? They win if they score, and that's it. So they're going to play normally if you don't get any points. The question is what happens on a field goal. Now, this gets a little bit more complicated, but not that bad. So if I get a field goal, what is the other team going to do? Well, they have two choices. Like they could either play aggressively, right? In which case they get a 50% chance to win, because if they get a touchdown, they'll win. But that also means they have a 50% chance to lose, right? If they don't score, they're going to lose. So if they play aggressively, they'll win with a probability of 50%. What if they play normally? Well, now they have a 1/3 chance either win, lose, or tie in phase one. And we have to be careful about thinking about what a tie means. But in phase one, at least, if they get a touchdown, they'll win. If they don't score, they'll lose. And if they get a field goal, they'll tie, and we'll move into phase two. So, what is their overall probability of winning? Well, in phase two, because we've already done that step of thinking about what everyone will do, everyone's going to play normally. And so everything that we've thought about from the original problem is going to hold, right? And from our perspective, if our probability of winning conditional on getting to phase two is 3/4, that means they win the rest of the time, right? Somebody has to win. So if I'm not winning, it's because the other team won. So they're winning with a probability of 1/4. We want to know what's the probability of winning if they play normally, given that I scored a field goal, right? Which I'm gonna denote like this. And that's just, well, it's the probability that they get a touchdown, which is a third, plus the probability that we tie in the first phase, which is that they get a field goal, also a third, times, and then 1/3 gets multiplied by the probability that they win in phase two, conditional on getting there, which is a quarter. And if you add all that together, that's 5/12, and that is less than a half. So they are going to play aggressively if they end up in a situation where I scored a field goal. So what should you do in phase one? Right? In phase one, I mean, we know what they're going to do conditional on you either getting a touchdown, a field goal, or not scoring at all, right? If you score, they're going to play aggressively. And if you don't score, they're going to play normally. So what should you do in phase one armed with that knowledge? Right? So if I play aggressively, there's a 50% chance I'm going to score a touchdown and a 50% chance that I'm not going to score. So here I'm going to try to figure out what's the probability of winning if I play aggressively. So if I get a touchdown, they're going to play aggressively. And if I don't score, they're not. And so I can think about what's the probability of winning? Well, that's the probability of winning conditional on getting a touchdown times the probability of a touchdown. I have to add to that the probability of winning conditional on not scoring times the probability of not scoring. So why does this equation work? Well, remember by the conditional probability rule I mentioned before, this first multiplication, that's just the same as the probability of winning and getting a touchdown. On the right, this product here is the probability of winning and not scoring. And since me getting a touchdown or me not scoring are the only two things that could possibly happen, then the probability of winning is just the probability of winning and each of the other kind of mutually exclusive and exhaustive sets of things I can do. So that's going to end up being the probability that I win in general. And I can get each of these elements separately, right? So if what's the probability that I win given a touchdown? Well, there's a 50% chance that they don't score, in which case I just win outright. If they do score, which also has a chance of 50%, then we have to go into phase two, right? And then I have to think about what's the probability of winning in phase two, conditional on getting there. And we already know that, that's 3/4. So I can add all this together and I get 7/8. So that's the probability of winning getting me a touchdown. What's the probability of winning given that I don't score? Well, if they score, then I don't win. So I don't like that. There's a 0 chance of me winning if they score, right? That does happen with probably one half, but since that multiplies by 0, I kind of excluded it. Then I have a chance of winning still, right? So there's a 1/2 chance that they don't score. And then we get to phase two, and then I can think about the probability that I win in phase two, conditional on getting there. That's just a half times 3/4, which is 3/8. So that's the probability of winning given no score, given that I don't score. And then I can add all these things together, and I end up with 5/8. That's the probability that I win if I go aggressive right at the start. Now I could just stop right here. So why can I stop right here? 5/8 is larger than 7/12. And 7/12 was the probability that we won in the original problem where everybody played normally. Now, what that means is the probability of winning if I play normally has to be no more than 7/12. Why? Why is that? The other team, they can't possibly do worse than the situation in which they didn't have the option to play aggressively, because they always have the option to not play aggressively, right? If they wanted to, they could always do the thing that they did before in the first Fiddler, in the non-extra credit, where they played normally and didn't play aggressively. So that's always an option for them. So by giving them an extra option, they can't do any worse. So my probability of winning, given that I play normal at the start, can't be any better than it was in the original Fiddler problem. So because the probability of winning, given that I go aggressive, is higher than the probability in the first problem, I know it's also higher than the probability of winning, given that I play normally in the first round here. So I could just stop here and say I should play aggressively and my chance of winning is 5/8. But just for the sake of completeness, I am going to figure out what the probability of winning is if I play normally, because this is going to again use that rule where I think about what's the probability of winning. I can think about probability of winning and all the possible ways that I could score or not in that first round of the first phase. And if I think about all of those separately and add them together, the probability of winning given those things, or of winning and getting those scores, that's just going to be the probability of winning. And so it's another kind of application of that idea. And here we've kind of already calculated all of these, right? The probability of winning giving a touchdown is 7/8, same as before. Probability of touchdown is now a third. Probability of winning giving a field goal is a half, which again we calculated before. Times the probability of field goal is a third. And also we calculated the probability of winning given no score. That is a quarter. And so if we add all that together, that's 13/24, which, as predicted, is less than 7/12, and as we know, is less than the probability of winning if we go aggressive, which is 5/8. So we should definitely play aggressively in the first round according to the simple model and only go for touchdowns. So that is the answer to the extra credit. Anyway, hope you got something out of this video, and I will see you again next week. Bye-bye. Bye-bye.